So we're back to multivariable calculus, and before I begin a new topic, I wanted to add a couple of things to our discussion last Thursday about formulas for the area in polar coordinates. Remember, we discussed polar coordinates. And one of the questions which arises here is to find the area of the following kind of picture. You have a curve which is given by the equation r equals f of theta, where r and theta are the two polar coordinates which we introduced last time, right? And in these polar coordinates, natural bounds for such an area would not be the vertical lines like x equal a, x equal b, the way we used to do it in rectangular coordinates. That's the old picture. Now it's more natural to give bounds in terms of the angle theta. So it's going to look like a sector like this between some angle alpha and beta. So we will assume that alpha is less than beta, and theta will be between alpha and beta. And so we look at this figure which is bounded by the lines theta equals alpha, theta equals beta, and the curve. This is the curve. And the question is to find the area of this. So I just briefly touched on this at the very end of last lecture, and I just wanted to tell you how to get this formula, which I wrote down without explaining it last time. So the idea is again to break this picture into small angles, which would be within some angle delta theta, and say here you'll have r, and just look at the area of this sector in the disk, right? So we approximate now our curve not by horizontal lines or line segments, but we will now approximate our curve by a small segment of a circle, because that's more natural. That's a more natural object in the polar coordinate system. Okay, so the question then becomes, what is the area of this little sector in the polar coordinate system? The analogous picture would be like this. So we'll have some delta x and delta y, right? And delta y, and so the formula for the area would be just delta x times delta y, right? And or more precisely, in fact, we don't look at it as a delta y, but we just look at it as a y coordinate of a graph. So it would be more precisely y times delta x, and that's what, after applying the procedure of breaking into small pieces, give us the formula for the area in terms of an integral like this, y dx. In other words, y delta x, the elementary area, gives rise to this integrand y dx. So we have to approach this problem in exactly the same way, but now instead of calculating this area right here, we need to calculate the area of this wedge, of this little sector. And this is actually not so difficult to do, because see, the point is that we know the area of the entire disk. So if you have a disk of radius r, we know the entire area. What's the area of the disk? Pi times r squared, right? Area is pi times r squared. And okay, so now suppose we're given, say, 1/4 of the disk. What's the area of this quarter of the disk? Will be 1/4 of this, right? So that would be 1/4. Why 1/4? Because the angle enclosed here is pi over 2, and so 1/4 is pi over 2 divided by 2 pi, which is the full angle of the disk. So in other words, if you want to calculate the area not of the entire disk, but of a part of the disk which is enclosed within the angle of pi over 2, you have to multiply this result, pi r squared, by the ratio of the angle which is enclosed to the total area of the disk. So it would be pi over 2 divided by 2 pi, right? So that would be 1/4 of pi r squared, which of course we knew in the first place, because clearly this is going to be 1/4, because there are 4 pieces which are exactly the same. But let's suppose you are in a pizza restaurant, and you have a piece like this with angle theta, and they didn't cut it in a very uniform way, so you don't know exactly. It's not pi over 4, it's not pi over 6, or pi over 3, whatever. And you want to calculate what area, how much pizza you got, and then compare it to how much your friends got. Say maybe they got more, so they should share, maybe give you back some. So what would be the answer? Well, we should argue in exactly the same way as before. Before, that angle theta was pi over 2, and what we did, we took the ratio between pi over 2 and 2 pi. And now instead we'll have a ratio of theta to 2 pi. That's what will represent the piece that we got, as opposed as a sort of the ratio of that piece to the entire disk, to the entire pizza. And therefore, the area would be pi r squared times theta divided by 2 by 2 pi, right? So pi cancels out, and you end up with 1/2 r squared times theta. That's the area of the sector of angle theta, which is exactly our question, except in asking this question, we called it delta theta instead of theta. So this area is 1/2 r squared delta theta. And that's the analog of this formula y delta x. So just like this formula y delta x gives rise to this integral, this formula for the elementary area of the elementary wedge of angle delta theta will give rise to the integral from alpha to beta 1/2 r squared d theta. You see, it's exactly the same, just kind of replace delta theta by d theta. And that's how we get that formula, which I wrote down at the end of last lecture. So to summarize, the key to calculating the areas like this is to break the figure that you got into small pieces, which will then look like elementary figures. Like in this case, would be an elementary rectangle, which is where I magnify, blow it up, and I show it there. Calculate its area, and then it gives rise to the formula for the area of a general picture like this. Whereas in the polar coordinate system, you do exactly the same, but you kind of follow the shape of the figure is different because the coordinates are now different. So now we split it into little sectors like this, where the angle is delta theta. I magnified one of those pieces right there. I found the area of that little piece by thinking about pizza and calculating it, right? And then I put all these little pieces together, and this gives rise to this integral. Okay? Any questions about this? So that's the way to calculate. That's the way to calculate the area in polar coordinates. And there's a similar formula also for the arc length in polar coordinates. But the formula for the arc length, I don't want to spend time on it, because we really take the formula which we derived in the rectangular coordinates about a week ago, and we just make the substitution where x is equal to r cosine theta and y is equal to r sine theta, and then just see what comes out. What comes out is some formula in terms of r and theta, which you can then use to calculate the arc length. So that's the way we do it for the arc length. Here it's more conceptual because we change the point of view slightly. Instead of looking at rectangles, we look at these sectors. It wouldn't be wise to try to break this into rectangles because they don't fit in this picture. What fits perfectly in this picture are these little sectors. So then we need to calculate the area of the little sector, which we've done here. Okay. So this, speaking of pizza analogy, these were the leftovers from last lecture. And now It's not what you say, it's how you say it. So delivery is so I'm working on it. Now, so now we move on to our next topic. And the next topic is vectors and geometry of space. And space here means three-dimensional space, which surrounds us. You see, up to now, in the last 3 lectures, we talked about objects which are defined on the plane. Here, I've been drawing curves on the plane. And we discussed various things about those curves, like arc length or various areas which are enclosed by those curves. But the basic point, the most important aspect of what we've done up to now in this class is the fact that we have worked exclusively with objects confined to a plane. And by plane, I mean this blackboard, or sort of an infinite extension of this blackboard in all directions. Right? All our objects have been defined on this plane. But now we want to move on, as I told you at the very beginning, in this class we're going to study not just objects on the plane, but also objects in space, in three-dimensional space. And because we live in a three-dimensional space, if you don't count the time. So in fact, we live in four-dimensional space-time. But that will be the topic for the next calculus class, I guess, four-dimensional space-time. Now in this class we do two-dimensional space, the plane, and three-dimensional space. So three-dimensional space is more interesting because it fits more objects. Now it fits not just curves, and there are a lot of interesting curves which appear in space, which are not confined in any particular plane. But also, perhaps more interestingly, it contains objects of dimension higher, namely two-dimensional objects, the surfaces, like a sphere, for example, or this wastebasket. These are all surfaces, if you ignore the fact that actually they have certain thickness. So what we'd like to do ultimately in this class is to understand the geometry of those surfaces as well as curves, and to be able to answer various questions about them, like finding their areas, and even more sophisticated things. So what we need to do now is to sort of lay the groundwork for this. In other words, we have to develop some formulas, because how are we going to represent curves? How are we going to represent surfaces in a three-dimensional space? What's the most efficient? So what we check for batteries before we begin. So in space, we need to develop some technique in order to attack these problems. And the very first thing that we should talk about is the coordinate system. Because, on the plane, it sort of goes without saying that we started out with, whenever I start drawing a diagram, drawing a picture, or drawing a curve, I draw this coordinate system. It's almost like a reflex. I usually call them x and y, the two coordinates. After last week, we're wiser now. We realize that this is actually not the only coordinate system that we have available for the plane. For instance, the polar coordinates provides us a different coordinate system. But this is a basic one, and we should start thinking about a similar coordinate system in the three-dimensional space. So this is the first step that we have to make. Coordinate systems. Now, of course, the problem is that even though I'm going to talk about the three-dimensional space, I'm still going to draw things on a two-dimensional blackboard, right? So of course I cannot draw this wastebasket on this blackboard. What I can draw is really a projection. So we create the illusion that there is some depth in the picture, and we try to imagine that the third dimension is there somewhere. So the way we usually would draw coordinates would be like this. So that, of course, the point is that they are not on the same blackboard. Only this one and this one lie on this blackboard, and this one is sticking out. It's sticking out, but we're looking at kind of slightly from above, and that's why it appears to us this way. So now we want to label these coordinates in a certain way. On the two-dimensional plane, we label them x and y. And in fact, some of you may have wondered why we label them x and y and not for y and x, not in the opposite order. Why not like this? Of course, in a sense, the notation is arbitrary. We have chosen these letters once and for all, so in a way, you can say that it's not a meaningful question because it depends on what we mean by x and y. But of course, what is important here is not so much which letters we use, but the ordering, the implicit ordering between x and y. X comes first and y comes second, because that's how they are ordered in the alphabet, right? So we could use y and z, and again, it will be assumed that y goes first and z goes second. So there is actually a basic asymmetry between these two coordinates, x and y. And we don't talk about this much. We haven't talked about this much when we talk about curves, but in fact, now is a good time to discuss this and to realize that there's a basic asymmetry. The point is that you could work with a coordinate system like this, x, y, or you could work with the coordinate system yx. And these are not equivalent to each other. There is no way to transform one into the other without removing them from this plane. Of course, if I were able to, maybe I should draw it more like this. If I were able to pick it from the plane and flip x and y, I would, of course, then, I would get back to this picture, x and y. That is a more traditional picture we draw, right? But we cannot flip them within the plane. You can argue, well, what if we just try to move these coordinates like on the clock and kind of move them and make them go through one another? But that's not allowed because then they have to pass through each other, and at that point they will cease to be a coordinate system. They will become parallel to each other. So that's not allowed. So in fact, if you think about it, you will see that there's no way to transform one into the other. There's no way to transform one into the other by moves confined to this plane. And that's a very important point, which tells us that actually our plane has two different orientations. Choosing one or the other, this coordinate system or the other coordinate system, gives it orientation. And the funny thing is, suppose that there was another class behind that blackboard, and there were people there, like a mirror image of this one, the bizarre world, if you will. And suppose there were kids, sitting there and also learning multivariable calculus. Then this one of them, the first one would appear to them as a second and conversely. I mean, not exactly, but if you rotate, that's exactly what you get. So, in other words, the orientation from this side, there's orientation from this side, when you look at the blackboard from this side, and there is orientation of the blackboard from the other side, from the bizarre world side. And these are two different orientations. These are two different worlds. And you can't transform one world into another within the plane, within the confines of the plane. If you go into the three-dimensional space, you can do that. You can just pick it up and flip them. But inside the three-dimensional space, you cannot do that. At first, it appears as a kind of a nuisance, and you may think that's not a very important point. But actually, in fact, for the plane, it's not so important. But in three-dimensional space, it becomes more important, and that's why we emphasize it. In three-dimensional space, we also have different choices of writing coordinates, labeling coordinates. And in three dimensions, we will label coordinates as x, y, z. And of course, again, the most important point is not so much which letters we use, but the ordering in which they appear. And the ordering, of course, will be the natural one, 1, 2, 3, just the way they appear in the alphabet. But then the question is, how do you assign? There are now many choices to assign these letters to the coordinate axis. And the question is, are we going to get always the same coordinate system? In other words, are we going to get coordinate systems which can be transformed one into another by moves within the three-dimensional space? And so now, since I've shown you that in two-dimensional space on the plane, that's not true. In other words, on the plane, there are two different coordinate systems which cannot be transformed into one another. You would not be surprised to know that actually here as well, in three-dimensional space, there are also inequivalent coordinate systems. But you might be surprised to know that again, there are only two choices, not more than two. So the choices are basically the one which we will always use will be like this, x, y, z. And the other choice which we will not use, which is not equivalent to this one, which is the bizarre world coordinate system, is this one. And then z again. In other words, we switch x and y, just we did before on the plane. Just the way we did before on the plane. If you try the other choices, for example, you put x, y, z like this, you will see that there are many different ways. There are 6 different ways to label them. You will see that that picture can be transformed by simple rotation into one of these two pictures. So really, there are only two equivalent ones, up to rotation within the three-dimensional space. If we could go into the four-dimensional space, if there were a fourth dimension that we could visualize, just the way we can visualize the third dimension when talking about the plane, we would actually be able to pick it up and transform one coordinate system into another in that four-dimensional space. But since we don't have a fourth dimension, or more precisely, the fourth dimension, time is kind of elusive. It's not easy to visualize it. So within the three-dimensional space, we cannot do that. So we have to agree from the beginning on what is the rule. What is the rule for labeling these coordinates? Because we have to do it now, because from now on we have to use the same system, so we are on the same page or on the same blackboard. Now, what is the rule? And so the rule is, there are different ways to phrase the rule. And the rule is in the book, it's explained by using fingers. But I always forget that. So I'll tell you the rule which I use, which is, I grew up in Russia. And we use the rule which is called the corkscrew rule. And this is not to say that Russians like to drink. But anyway, it is called the corkscrew rule. And the way it works is like this. If you rotate the corkscrew from x to y, so here's the corkscrew. I kind of draw the basic one. If you rotate it from x to y, then the thing will go in the direction of the z axis, right? In other words, if you, well, it's not a good picture because then the bottle will have to be upside down, but you see what I mean. So if you think about the corkscrew going from x to y, which is natural, right? Going from x to y is like going from the first coordinate to the second. Making rotation as if you were moving the x coordinate system to the x axis to the y axis, then the screw will move in the direction of the z axis. So that's the rule which I find easy to remember, even if I don't have a corkscrew on me. It's easy to remember. But you can use whatever rule you want. You just have to remember that there is such a rule and to draw this picture in this way. Okay, so that's the first point that we have to make about this. The second point is we have to develop some tools for representing objects in space. Okay. So the first, I already told you that the objects will be mostly interested in. I'm still looking for battery, but I guess no luck. So the objects that we are mostly interested in are curves and surfaces. But in fact, there are simpler, more elementary objects, namely points. So before we talk about these complicated matters like curves and surfaces, let's talk about points. In the case of a plane, we know how to represent a point. We just drop the perpendicular lines onto the x and y axis, right? And say we get x0 and y0, and we represent the point as x0, y0 like this. And we're going to do the same in the three-dimensional space. So I draw the same coordinate system, and I'm thinking, okay, if I go from x to y, it's going to z, so that's how I should put them. Because if I put them the other way, I would have to move the corkscrew this way, and it would go down. So z would have to go this way. So this is a good orientation. This orientation we've chosen. And our mirror image will have the opposite orientation. So if we have a point, we also can represent it by its coordinates. And now there are going to be three coordinates, obviously, because we're in three-dimensional space. And the way we find these coordinates is as follows. We drop the perpendicular line from this point to the plane, x and y. Now, at this point, you have to use your imagination, and you really have to think of x and y as a plane which is sticking out like this. And the point is actually not here. It's not in the zy plane, but it's here. So you've got, I can't show you because one of my hands is busy with the microphone, but you can see, I'm trying. So this is a plane, and the point is here, so you drop the perpendicular down, like this. So you get a point on the plane, which is the xy plane. Now, I draw it like this. So the point is somewhere in space, and that's where it drops. So now I get a point in the xy plane. But a point in the xy plane we already know how to represent. We just drop the perpendicular lines to the x-axis and the y-axis. So what we got already is y0 and x0, coordinates of this point. The two of the three coordinates. What about the third coordinate? It is tempting to draw a perpendicular like this, but that's not true, right? To give it really a depth, to give it the illusion of a three-dimensional picture, I have to do it in the following way. I have to connect the origin to this point, which is the point I got by dropping my original point on the xy plane, and I have to connect to the z-axis by a parallel line. So this one and this one are parallel to each other, and that's going to be the z0 coordinate. You see, the point is that this is perpendicular to this entire plane, so in particular it's perpendicular to this. And that's why the z-axis is perpendicular to this line. So what I'm doing really is I'm dropping perpendiculars to each of the three coordinate systems. But the way I draw it is slightly complicated because I'm using two-dimensional projection of the picture. It would have been much easier if I had a three-dimensional model of this whole thing. So then you would see more clearly what the coordinates are. But I think it's fairly self-explanatory here. So if we have this picture, then we will say that the point has coordinates x0, y0, and z0. And this is in complete analogy with the situation that we have, the picture that we have in two dimensions. So nothing surprising here. What else do we need to know? We need to know the distance between 2 points. Right? So for instance, we would like to find oftentimes, let me use a different chart. Oftentimes we might want to find the distance from